Today we have Sylvain Courte from Grenoble, who will talk about twisted generating functions and the nearby Lagrangian conjecture.
Okay, so thank you very much for inviting me. It's a pleasure to give this talk. So I will indeed report on some joint work with Mohamed Abu Zaid, Stéphane Guillermo, and Thomas Crabb. So the paper is on the archive for a few months. Okay, so I will start with introduction. Okay, so so there is this very famous conjecture in symplectic geometry, which is very stimulating for the community, the so-called nearby Lagrangian conjecture. So I'm recalling the statement. So let M be a closed manifold. Okay. And L inside of the cotangent bundle of M is a closed, so by closed I mean compact without boundary, exact Lagrangian submanifold. Then such a submanifold should be Hamiltonian isotopic to a zero section. That's the prediction. So Hamiltonian isotopic here means the same as isotopic through exact Lagrangian submanifolds. Okay. So it's a very hard problem. Not, but there have been many results on partial results on this. So first, it's known to hold only for a few manifolds, but just 3 manifolds, I think. M is S1, S2, and T2. I think that's the only manifolds where the result is known. But there are partial results, like for example, the result that the projection from L to the base, M, is always a homotopy equivalence. This is going to be important for what I will discuss. So this was proved by Abu Zaid and Crabb using Floer theory. And also, I mentioned that this was reproved by Guillermo using microlocal sheaf theory. Okay, now another result also is that, which will be very related to my talk, is that if the conjecture holds, so if the Lagrangian is Hamiltonian isotopic to a zero section, then L can be described by a generating function. So that's a result of Jean-Claude Sikorav. So a generating function, which moreover is quadratic at infinity. So I will explain in a moment the definition of generating function if you don't know it. So that follows from theorem of Sikorav. Okay, so if you believe in the conjecture, then there should be a generating function for any nearby Lagrangian. Okay. And now the last result I want to mention is a result of Stéphane Guillermo, which says that L admits a generating sheaf. So by generating sheaf, I mean it's a sheaf on M cross R with micro support L, essentially. Okay, so this was proved by Guillermo also. So now it's tempting to ask this question, which is still open. Okay. does L admit a generating function? Okay, so it's like a two-step program, maybe for the conjecture. Try first to produce a generating function and maybe then use it to prove the conjecture. It's very optimistic. I don't know how to do it, but I will focus on this first step. Construct a generating function. Try and construct a generating function for L. So I will abbreviate as GF. Okay. So this is still open, but we can prove the following theorem. So okay, I have to say myself, Guillermo and Craig. So in the same hypothesis as the nearby Lagrangian conjecture, L always admits what we call a twisted generating function. It's not going to be quadratic at infinity, but some other condition, which in particular is a well-behaved generating function, which we call of tube type. So I will explain what this means. But it's kind of, I mentioned that it's a well-behaved generating function. Okay, so a corollary of this result is the following. There is associated to the Lagrangian L, there is the stable Lagrangian Gauss map. So you think of the tangent spaces to the Lagrangian. So they live in some Lagrangian Grassmannian bundle over T star M, but you can trivialize the things and then define a map, a Gauss map from L to U mod O, which is the stable Lagrangian Grassmannian. And so we can prove that this map vanishes on all homotopy groups. Okay. So if you believe in the nearby Lagrangian conjecture, then it would imply that this map is null homotopic. Okay, so we prove something which is weaker, the fact that it vanishes on all homotopy groups. Okay, as a consequence of this construction of a twisted generating function, as I will explain. So now, for example, a corollary of the corollary, if M is a sphere or homotopy sphere, if you wish, then vanishing on homotopy group is good enough. Okay, and we get that this map is null homotopic, and we construct a genuine generating function, untwisted somehow. Okay, and construct a genuine generating function. Okay. So basically, the rest of my talk is going to be about the proof of these results. I will try to explain as much as I can about this. I want to also mention some work in progress with Danny Alvarez Guevara, where we use this generating function to give new restriction on the smooth structure of L. In particular, for exotic spheres. I mean, we can exclude a few exotic spheres from the one that can be embedded in T star Sn. Okay, so new restriction on the smooth structure of L. So in particular, the question which homotopy sphere sigma n can be embedded into T star Sn. Okay, so the generating function can also be useful to say something about that smooth structure. Okay, is there any question so far? So this is just a bunch of results. Now I will explain the words involved and everything. So, okay, I will start now. First part about twisted generating functions. Twisted or not, I will start with regular generating functions, and then turn to this twisted notion. Okay, so I recall what is a generating function. So you're given some open set in M cross Rm, and a function on real valued function on U. Okay, and associated to this, there is a singular set sigma f. So it's a set of fiberwise critical points of f. So a set of QV in M cross Rn. Q is on the base and V is auxiliary variable, such that df over dv at this point is 0. Okay. So I will assume always that this equation is a regular equation. So this defines a submanifold. Okay. And now this submanifold comes with the Legendarian immersion inside of the one-jet space of M, okay, which is T star M cross R. This is just given by QV maps to Q in the base, df over dq, the covector, so at the point QV, and the value of the function f of QV. So this is the fact that this map, which I will call maybe I sub f, this is always a Legendarian immersion. So in fact, if you take a generic function f, it's going to be an embedding, okay, but in general, it's just an immersion. And this Legendarian immersion is said to be generated by this function f. So we call f a generating function for this Legendarian immersion. Okay, so I will give an example. Now, so take, for example, this function from R2 to R, given by f of qv is v cubed plus q squared minus 1 v. Yeah, let me put a 3 here. So what is this singular set? So the set of fiberwise critical points is a set of QV such that 3v squared, so you get v squared plus q squared equals 1. Okay, so it's a circle. It's a circle in the QV plane. Okay, I'll write this one. And I've said that this has a natural Legendarian immersion. So now this Legendarian immersion, I will just draw the front projection. So in M, which is R, here in this case, in M cross R. So in M cross R, what you see is this flying saucer. Sure. Okay. And now such pictures are familiar in the study of parameterized Morse theory. So one way to think about generating function is as a family f sub q of maps from Rn to R, with q varying in M. And now the link with symplectic geometry is that what is called the self diagram of this family FQ. So this self diagram is the graph of critical values of FQ, is the same as the front projection of the Legendarian so IF of sigma f. This map is IF. Okay, so maybe I can draw this family of function So on the left, it's like an increasing function, so no critical point. And at the cusp, there is a cubic critical point like this, then 2 critical points, and then the critical point is degenerate again and disappears. So you see the graph of critical values will be like that. Okay. Okay, so that's the notion of generating function. I will remark that I have defined a generating function here just on some open set of M cross Rn. And this will be useful because I can now restrict to a neighborhood of sigma f. In fact, if I just define f on small neighborhood here, I will generate the same Legendarian. Okay. So you could think of this neighborhood U, where the function is defined, as just a tiny neighborhood of sigma f. Okay, that's the kind of generating function I want to work with for a start. Just as I think of it as just as a germ along the singular set. Okay, so for the moment, so I mentioned this because it's a very weak notion of generating function. You cannot really do anything with that. So at some point we have to convert it into a better behaved generating function. So U can be a tiny neighborhood of sigma f. Okay, so it's a weak generating function. Okay, so far so good. Okay, now if you're given a Legendarian, you can ask yourself, can I describe it by a generating function? So the answer is no in general. Not all Legendarians are like this. So it's easy to see a first obstruction. For example, in S1 cross R, I draw a Legendarian like this. So the base is S1. So the left is identified with the right. Now, this front corresponds to the graph of a critical value. So it has a Morse index. So maybe this branch corresponds to a critical point of index I plus 1. This one is of index I, and this one is of index I minus 1. Okay, necessarily. But now I minus 1 is different from I plus 1, right? So it's not possible to put Morse indices in a coherent way, continuous way. So this is an instance of the first mass of class obstruction. Okay, so given the genre like this, you have a class mu1 in a H upper 1 L with coefficient in Z, which is the first mass of class. And this class has to vanish if F has a generating function, if L has a generating function. Okay. And this Z, you should think of it as a pi1 of U mod O. And in fact, mu1 is the obstruction to the triviality of the Gauss map on the one skeleton. Remember, L comes with a map to U mod O. And this is the first obstruction. If you want to produce a null homotopy of this map, you try to do it on the one skeleton and you face this obstruction. Okay. Now what happens in the higher dimensions? Well, in fact, the whole map itself is the obstruction. So there is a theorem by Giroux and Latour independently in around 90, which says that so a Legendarian immersion L to one-jet space of M admits a generating function. So again, in this sense, this kind of weak sense, if and only if the Gauss map is null homotopic. Okay, so that's the relation between generating function and the stable Gauss map. Okay. Now, if we come back to the nearby Lagrangian conjecture, if L is a nearby Lagrangian, so it's unknown whether the Gauss map is trivial or not, but what we know, so this is, as I mentioned, is still open. But what we know is that the projection to the base is a homotopy equivalence. Okay, that's the result of Abu-Zaid prime. Okay, we know this map from L to M is a homotopy equivalence. So the idea is that we are going to, so we can factor the map through M up to homotopy. Okay, by taking a homotopy inverse of this projection. So we are going to use this map from M to U mod O to somehow twist the generating function. Okay, so that's what I will define next. So we will use the map M to U mod O to kind of twist a generating function. I will explain what I mean by that. Okay. Are there any questions?
Sorry, Sylvain, I have a quick question.
Sure.
I have a question about this theorem of Giroux. Can you go back up?
Yeah, sure.
What about for, so this condition that L to U mod O is null homotopic, that's kind of a condition about formal Legendrians, right? So in high dimensions, there's these, I'm a little bit confused because there's these loose Legendrians, which are in the same formal class as the original Legendrian, and they also don't have generating functions.
Yeah, right. But that's as I said, it's a very weak notion of generating function. So when you think that when you say that loose Legendrian do not have generating function, in fact they can have generating function in this weak sense. But they must badly behave at infinity. Okay.
I see. Thank you.
Okay. Okay, so I will now try to give the idea of what is a twisted generating function through one example. So I take the same example before. So we said that for this guy, it's not possible to have a generating function because there is a Maslov class obstruction. Okay, so here M is again S1, and now the idea is that I will cut this in two intervals, M1 and M2. Okay, so maybe M1 is going to be this interval, and M2 and another interval like this. Okay, so there are two connected components of the intersection. Here maybe I call this M12 plus, and the other intersection is M12 minus. Okay, so a twisted generating function is going to be a generating function on each open set which glue up to stabilization by quadratic forms. So it's going to be a function f1 on m1 cross some r n1, say, to r. Another function on m2 cross r n2. So these are going to be generating functions, okay, which generates this Lagrangian over everything that's over the open set m1 or m2. Okay. And I will also have, so I will, in this case, I I can imagine that n2 is going to be n1 plus 2. Okay. So say the indices are I plus 1. So for the function f1, it will correspond to a critical point of index I plus 1, I and I minus 1. But for m1, it's going to be I plus 1 on the left. So on m1 2 minus, it's fine, they coincide. But now in this on the right, m2 is I plus 1. So I have an issue here. I minus 1 is different from I plus 1. So I will have to do something on m1 2 plus to compensate for that. Okay. So I will need a quadratic form to shift the indices. So Q12 is going to be family kind of fiber-wise generating quadratic form, so fiber-wise non-degenerate quadratic form on R2. Okay, which may depend on the point of the base. Okay, and in fact I can take it so that Q12 of Q is the point in the base. It's nothing to do with the quadratic form. Of UV are the coordinates in R2, is going to be so U squared plus V squared, so positive definite quadratic form when X is in M12 plus. Or M12 minus, I want to, let me think. M12 minus, yeah, and minus U squared minus V squared when X is in M12 plus. Okay, so this is in such a way that you may now have F1 plus Q12 equals F2. Maybe I will dezoom a bit. Yeah. So you see, F1 and F2 have the same index above M12 minus. So, and they differ by Q12. Q12 has index 0 on M12 minus, so it's fine, it's not shifting the indices. While on M12 plus, F2 has Morse index 2 more than F1. And this is compensated by this change of quadratic form, which is negative definite. Okay, so I mean, I'm not saying that, claiming that, I mean, it's not easy to, or it's not obvious that such a generating function exists, but now there is no kind of Maslov class obstruction. Okay, this Q12 is kind of solving the issue of the Morse indices. Okay, so now this is in dimension 1. There's the Maslov class is the only issue, but now in higher dimension you can imagine that you have higher abstractions. So it will be encoded in by families of quadratic forms like this. Okay, so now I come to the actual definition. So a twisted generating function. So it's the following data. It's first an open cover of M. And I want the indexing set I to be ordered. Okay, this has some importance. And now for all I have a generating function defined above Mi. Okay. And on all double intersection, for all I less than j, I have a Qij above Mij is the double intersection to R on Nij to R, which is a fiber-wise non-degenerate quadratic form. Okay, and now this is subject to the following condition. So first, for all I less than j, you should have fi plus qij equals fj. So the generating functions fi glue up to this quadratic form qij, and this qij should satisfy a cocycle condition that qij plus qjk is qik. Okay. So that's the definition. So right, this is valid on mij, and this is on the triple intersection mij. Okay. So the twisting. So what we use to twist is this this quadratic forms qij, and also the integers ni for each generating function is defined on some r to the ni. Okay, so you have these integers ni and quadratic forms qij. So this is what I will call the twisting datum. So this looks like a bundle data. It's the way that you describe a bundle in charts. Except that the cocycle qij is not valued in a group but in a monoid. So it makes the theory a little bit more complicated. So that's why I need the indices to be ordered, because there is no qij minus 1 somehow. So it looks like a bundle. Okay, except that qij is valued in a monoid. So the monoid, which I will denote q, is just the disjoint union for all n of consider all non-degenerate quadratic forms on Rn. Okay, and this is a monoid for the direct sum operation. If you have one on Rn and one on Rm, you get one on Rn plus n, right? Operation is just the direct sum. Okay. So it's a monoid, but it's not really a problem. I mean, there is a theory of bundles with kind of principal bundles with a monoid instead of a group. In particular, there is a classifying space for such thing, which I will note by BZQ. So there is a simplicial construction of this space, which is canonical. There is, it turns out that this space is precisely U mod O, the Lagrangian Boltzmannian. So this is kind of an instance of Bott periodicity, in a sense. So this space, classifying space BZQ, is homotopy equivalent to U mod O, turns out. So the twisting datum that we need to define a twisted generating function is classified precisely by a map to this classifying space, so by the Gauss map. Okay. The twisting datum is precisely given by a map from the base to U mod O. Okay, so and now in the case of a nearby Lagrangian, since the projection from L to M is a homotopy equivalence, then the Gauss map is perfectly this twisting datum remembers the Gauss map perfectly. Okay. So this encodes perfectly the Gauss map L to U mod O, at least for a nearby Lagrangian. Okay. since we know that L to M is a homotopy equivalence. Okay, so this will not solve, I mean, you cannot define twisted generating function for all Legendarian, because, for example, if the projection from L to M is null homotopic, say, for example, if M is R, for example, if you have a Legendarian knot like this, so in this case, you also have an issue with Morse indices, right? But in this case, the projection to the base, which is R, is null homotopic. So in this case, twisting cannot help to define a generating function. Okay, so it's important that somehow the non-triviality of the Gauss map can be encoded in the base. Okay, and okay, so for this knot, no generating function exists, even twisted. Okay. But now the result that we can prove is, so it's a generalization of the result of Giraud and Latour. So we prove that a Legendarian immersion admits a twisted generating function. So again, it's in this weak sense, right? So no well behavior at infinity. If and only if the Gauss map factors through the base at 2 homotopy. Okay. So in the case where the Gauss map is null homotopic, then this is of course true. So it generalizes Giraud and Latour as a result. Okay, now as was already mentioned, the problem with all this is it's kind of formal, as Oleg was saying. So this notion of generating function is too weak. You cannot use it to prove anything. You know, so people are used to work with generating functions quadratic at infinity, for example, or other conditions. So you need something of this kind. So this is provided by the following trick that I like to call Guillermo's doubling trick. So this is a trick that Stéphane Guillermo used in his construction of a sheaf. I said at the beginning that a nearby Lagrangian always has a generating sheaf. So he proved this using the following doubling argument. So given a Lagrangian L, or Legendarian, say, the lift of a Lagrangian, you can always take a 2 copy of this thing. So you push it slightly in the R direction, up, and you define this L epsilon, which is the 2 copy of L. Okay. And now what Stéphane proved is that any kind of micro-local sheaf on L can be converted into a genuine sheaf for the 2 copy. So by genuine sheaf, I mean a sheaf on M cross R with micro support, the 2 copy, L epsilon. Okay. Now we asked ourselves, okay, does it hold also for generating function? And in fact, it does. So the same principle, and it's a very easy construction. I will explain now. So the same principle holds for generating functions, where microlocal generating function is precisely what I was discussing before. So just a germ of generating function near the singular set. as in the Giraud-Latour theorem. The singular set sigma. Okay. Okay, so how does that work? Maybe I can pause for questions. Is it fine? Okay, so I will try to explain how to turn a
Questions
germ.
from chat.
Yeah, I'm not looking at the chat, so
I can read it to you.
yeah, please.
This example is stabilization of unknown. Since loose Lagrangian are also some sort of stabilization, is there some obvious reason why it admits this weak generating function?
Stabilization of unknowns. Yeah, so, okay. I've been drawing this zigzag, which is in fact indeed an abstraction to have a well-behaved generating function. But yeah, as I said before to Oleg, this is not, this zigzag is not an abstraction for this weak, because these weak generating functions, they just care about the Gauss map, about kind of how the tangent space to the Lagrangian is turning inside of the Lagrangian Grassmannian. It doesn't care about kind of rigidity phenomenon. It's just some formal thing about the tangent bundle. Yeah. Okay, so how to convert a germ of a generating function into a well-behaved generating function for the double. So okay, so let f from u is an open set in M cross Rn be generating L. Okay, so I have a picture like this. This is M cross R. I have a singular set sigma f, and the function is maybe defined on a very small neighborhood of sigma f. Right, this is my open set U. Okay, so the first step is to extend f arbitrarily to a function, so f tilde from M cross Rn to R. So this is a very violent operation. When you do that, you will create many new components in the singular set, probably, unless you're very lucky. But... okay, so you get extra undesired Legendarian. Okay. Okay, and now in the next step, we are going to remove this extra Legendarian. So we add one variable and define f epsilon on M cross Rn cross R. So I take one new variable, and with the following formula, so f epsilon of q v w, w is the new variable, so it's just f of qv plus w cube minus epsilon alpha of qv w. So this function w cube minus w, is this function on R with two critical points. And now, depending on the sign of alpha, if alpha is positive, it has two critical points. If alpha is negative, there's no critical points. So this alpha is a cutoff function, which is going to be 1 near sigma f, and it's going to be negative away from the open set U. So now, if I do that, you see that the derivative with respect to W of f epsilon is going to be positive away from away from this open set U. So all these extra components are going to disappear. Okay, so df epsilon over dw is positive if qv is not in U. Okay, so essentially in my picture I'm adding one variable. Oh, so this was Rn, sorry. So I'm adding one more variable, and in the region U, when qv is in U, I have a function of w of this type with two critical points. So this will generate for me the two copy of L. And as soon as I go away from U, I have an increasing function of the variable w. So this extra Legendarian disappears for f epsilon. Okay, so it's a simple trick. And we get that f epsilon generates the two copy L epsilon. Okay, and what we have gained is that now f epsilon is well behaved at infinity. In fact, it is essentially linear at infinity. So essentially, f epsilon is equal to w at infinity. So it's the class, or it's not exactly equal to w, but derivative with respect to w is positive, so you could interpolate between f epsilon and w outside of the compact set. So this is the class called the linear at infinity functions. Okay, so that's the Guillermo's doubling trick for generating functions. So this works for any Legendarian immersion. Okay, but now the next step is to let epsilon increase. Okay, this works just for a small epsilon. Now, if epsilon goes to plus infinity, what's happening is that L epsilon is going to be a regular homotopy. So it's a family of immersions. And moreover, the crossings that appear during this regular homotopy, they are in one-to-one correspondence with the rep chord of the original L. So it's like, for example, if I do it with an unknot like this, I have just one rep chord. So I take a two copy, and I separate them progressively, and at some point, it's kind of, there's a critical moment where there is a double point for L epsilon, okay, because there are two branches of the front which intersect and are tangent, okay, and after a while they are completely separated, okay. So this is the separated two copy, okay. Now, what's nice in the setup of the nearby Lagrangian conjecture is that there is no rep chord, okay? Because by definition, you start with an embedded Lagrangian in T star m. So it's a Legendarian lift. It's a Legendarian without rep chords. So this movie L epsilon is in fact a Legendarian isotopy. Okay, so this was also exploited by Stéphane Guillermo in his construction of a sheaf. So we are doing the same thing. And now, kind of fundamental result of generating function is that there is a homotopy lifting property. Okay, it was first proved by Sylvain Courte in the case of Hamiltonian isotopy, and for contact isotopy by Chekhov. So this Chekhov theorem. Generating function in a sentence is just generating function persist up to stabilization, I should say. So maybe you'll have to introduce more variables. Persist up to stabilization under Legendarian isotopy. Okay, so I have constructed a generating function for the 2 copy with epsilon small. And now during this movie, there is no bifurcation. It's always an isotopy. So I should obtain a generating function for the separated 2 copy. Okay. So we had to prove this result in the case of twisted generating function. And okay, so it also works. So this principle is also true in the case of twisted generating functions. Okay. So I get, okay, so we get, maybe if I draw like the picture like this of a nearby Lagrangian, get a picture like this. Okay, and after a while, they're completely separated. Now I can cut at a level, say 0. One part of the front is in Z negative, and one part in Z positive. Okay, so I can restrict to this part Z negative, and I will generate just 1 copy of the Lagrangian, of the Legendarian. Okay, so we get, at the end of the day, we get a twisted generating function for just 1 copy by restricting to Z negative. Okay, I forget about the rest, Z positive, and I get a nice generating function for L. Okay, so how does it look like? So, is it like quadratic at infinity or something like that? So not quite, but it's okay, a kind of function which in fact has already been studied by notably by Waldhausen in his study of algebraic Kessier spaces. So this is related to what's called a tube space, what I want to explain now. And we're going to use an important result of Buckstedt about this. How much time do I have left? Like 5 minutes more or less. Okay, so I'll try to be quick. Okay, so first, okay, we have this generating function for this separated 2 copy. First thing that we do is we show that, okay, this is on the base M. So for each Q, I get the FQ negative. So this part. Okay, so in the fiber, I take the level set FQ negative. And we show that the homology of this relative to FQ is minus infinity, is in fact isomorphic to Z. It's in some degree. Okay. And also the level set FQ equals minus infinity is essentially the same as W equals minus infinity, because F was linear at infinity. So this is Rn. Okay. So when I consider the level sets of FQ, I start with Rn, and then there is a cobordism with homology equal to Z. Okay. So now by by following the H-cobordism theorem proof by Morse-Mills theory, we can show that in fact this level set is just Rn. Let me write it there instead. is just Rn cross minus infinity 0, union just one handle to generate the homology, the one trivial handle. So this is how the sublevel set looks like. So there is some Rn, hyperplane in Rn plus 1, and you attach just one handle. So it's something in Rn plus 1 which is isotopic to the attachment of just one handle of some index. So maybe this is, so there is some disk, attaching disk dk. Okay. So trivial index, say of index k. Okay. And as I said, so this was considered by Waldhausen. He considered the space of all such hypersurfaces. So the hypersurface FQ equals 0. Inside of Rn plus 1. And it comes with a map. So this space, we call it T sub Kn. Okay. It comes with a map from the Grassmannian of K-planes in Rn. So from GKN, so Grassmannian, to TKN. This is because you can rotate around. In Rn, you take a K-plane, which you can rotate in Rn, okay, in this space, in this Grassmannian space. Then you can attach a handle along this unit sphere in Rk plus 1. And you take like a standard neighborhood of this thing. Okay, so to each K-plane you attach a kind of canonical hypersurface in Rn plus 1. It's not completely canonical, but you can fix a way to do it. And okay, so this is called a rigid tube map. Or at least when you go to, you can stabilize and go, let K and N go to infinity. And now it's going to be a map BO from BO to T infinity. This is the limit of this thing. Okay, because when you study generating functions, you can always stabilize, so you can assume that N is very large and K is very large. So only the limit is meaningful somehow. And there is a result by Buckstedt that this map is in fact a rational homotopy equivalence. Okay, and the consequence of this that we will use is that in particular it is injective on all homotopy groups. Okay, so this means that if you have like a sphere of K-planes rotating around in Rn, if it's non-trivial, it's also going to be non-trivial in the space of hypersurfaces. Okay, so it's not at all obvious. This is a deep result. Okay, and now the end of our proof is that okay, so going back to our twisted generating function. So we have Fi and Qij. So above each Mi, we have this function Fi, which defines a map into this space of hypersurface. So you get Mi into T infinity by, this is the map which is a sublevel set Fi, or Fi equals 0 maybe. So hypersurface Fi equals 0. So this does not define a map from M to T infinity, because we have Fi plus Qij equals Fj. The functions F do not actually glue, but they glue up to this Qij. In fact, this means in fact that they glue up to the image of this rigid tube map. So this will assemble into a map from M to so B T infinity Q. Q is this monoid of quartic form, or if you wish, it's the homotopy quotient of T infinity by BO. Okay. And this map factors the Gauss map. Okay. If you forget about the maps Fi and just remember the Qij, you go into B ZQ actually, which is U mod O, as we saw. So there is now a last diagram, and I am done. So I write BO inside of T infinity. This is the rigid tube map. I have the quotient T infinity mod BO, and here U mod O. Now this is set up so that the Gauss map is this map from M to U mod O, and the construction of a generating function, in fact, is a lift of this map here. This twisted generating function defines the lift here. Okay, and now the conclusion on the Gauss map, okay, comes from the fact that if you go to pi I, by Buchstedt theorem, this is injective. So this means that the map, the previous map was 0 here, because the next one is injective. So this one is also 0 on pi I, in fact. So we obtain that the Gauss map, which is a composition L to U mod O, vanishes on all pi I. Okay, now we'll stop here. Thanks for your attention.
Thank the speaker. Is there any questions for Sylvain?
I wanted to ask something. Just for the homotopy lifting property at the level of twisted functions, is there any subtlety, or does the QI just come along for the ride?
It's not so easy. In fact, yeah, we had some headache for proving it actually, because you have to work with this set of indices I and the Qij. So no, it's not true that or we could not do it actually to prove that directly that all Fi are going to persist, and with the condition that Fi plus Qij equals Fj. So we could not do it directly like that. So what we do is we take a Legendrian isotopy and we fragment it as a composition of isotopies with support in balls, as a product of, you cut off the isotopy in using a covering by small balls, and then we do it one ball at a time actually. And we have to, at each step, we have to rearrange the quadratic forms Qij. So no, it's not so easy, in fact, as we do it at least. Maybe there's a simpler way, but no, it's not so easy actually. Yeah. But it follows from the untwisted result. Okay, plus some tweaking with quadratic forms. There's nothing really deep in this, but not so easy to write it down.
Any other questions?
Yes, for usual generating functions, one can look at Morse homology, right? And then you recover somehow Lagrangian for homology. And I wonder, do you have some similar story for this twisted case?
For twisted case, yes, yeah, I think, in fact, right, when you take what you usually do with generating functions, if you want to obtain homological invariance, you take a difference function, right? So you take f. So if f is on M cross Rn, then what you define is M cross Rn cross Rn you take the difference function, right? F of QV minus F of QV prime. Okay, and when you do this difference function, delta F, in fact, even if F is just a twisted generating function, the difference function is going to be untwisted because it's like F minus F, right? So the twisting actually disappears when you do this. So what you usually do with the difference function of generating function can also be done with twisted generating function. And in fact, we use it in the paper at some point to prove that the homology is concentrated in 1 degree is equal to Z. Yeah, this result is based on the difference function. Yeah.
Okay, great, thank you.
Maybe more questions? If not, let's send the speaker again.
Thanks.